Hello everyone and welcome back. My name is Mr. Kowalt, and in this video we're going to go over using the Henderson-Hasslebach equation for creating a buffer by partial neutralization. So let's get into this. So in this problem we're going to create a buffer by partial neutralization, and then we'll see if we can use the Henderson-Hasslebach equation. And then I'm going to go over 4 methods that you can do to solve this problem. So let's get into this. So I have a solution. It says it is created by adding 10.0 milliliters of 1.00 molar HCl, which is a strong acid, to 200 milliliters of 0.20 molar ammonium, NH3, and then it asks, what is the final pH of the resulting solution? So the first thing we notice is that we don't have any conjugate acid here. We just have the NH3. So you might think that this is not a buffer problem, but you have to recognize that you are adding a strong acid to the mixture, and then that strong acid is going to react completely with the weak base, thus creating the conjugate acid, and thus we're going to create a buffer. So this is a buffer problem. It's just going to be created in the process after you add the acid. So what we need to do is, first we would do an IF table or ICF table, do the stoichiometry first using moles or millimoles, and then go from there. So the first thing I want to point out is that this is going to go to completion, and we can identify that or prove that in the following way. So we know that Kw is equal to Ka times Kb. Ka and Kb are the K values for the acid and conjugate base or base conjugate acid pair, and so they are related to each other by this equation. And so we can look up the Kb value for NH3. And so when we solve this equation for Ka, we get Kw over Kb. Kw is 1.0 times 10 to the negative 4. That is just common knowledge in the chemistry world. And then we have Kb. We looked that up. That's 1.8 times 10 to the negative 5. We divide that, we get 5.55 times 10 to the negative 10. And so this is the Ka value for the conjugate acid ammonium, which is NH4+. So we have our equation here where we have this strong acid in the form of hydronium ions reacting with the weak base to form the ammonium ion, which is the conjugate acid, and water. And so we can figure out what the K value is for this reaction by noticing that here we have the NH4+, the ammonium ion, the conjugate acid, reacting with water to reform the NH3 and the H3O+. And so this, if you recognize this equation going this way with these two reacting to form this is the definition of the weak acid reacting with water to get the Ka value for the NH4+. So anytime you have a weak acid reacting with water, the K value is the Ka. So that's the way Ka is defined. It's the acid or weak acid reacting with water to give whatever the products are. In this case, conjugate base and water, or conjugate base and the H plus ion. And so if we recognize that going this way, the K value is Ka, therefore, the K value going this way is going to be the reciprocal of that. So K for this reaction is 1 over the Ka of NH4+, which we just calculated here. And so now we can plug that in over here, and then we get the Ka value for this reaction. And I want to point out that, look, that power there is a power of a positive 9. This is a very huge number for K, which indicates that this reaction favors the products very, very much. So it's pretty much going to go to completion. This way, all of this is going to react with the weak base to form all of this. So basically, at equilibrium, this is going to be 0. So therefore, we do a stoichiometry table first. We don't do our ice table right away because this is going to be going into completion. We have to do the stoichiometry table or IF table or this ICF table if you want to put it that way. So let's go ahead and do our ICF table. So here, I'll write it out, ICF, where I is the initial amounts that we were given, C is the change, and F is the final amounts. Now in this case, we don't want to use molarity, we don't want to use concentrations, we use the moles or millimoles. So let's go ahead and do that. So we're going to calculate the millimoles. So for the millimoles of the strong acid, you take the volume in milliliters, multiply it by the molarity, you get the millimoles. So 10.0 milliliters times 1.00 molar is going to be 10 millimoles. So we're going to have 10 millimoles of our acid. And then if we have 200 milliliters, we're going to multiply that by the molarity 0.20 molar, and we get 40 millimoles of our weak base. So we're going to have 40 millimoles here. And of course, we're starting with 0 here, 0 here. And so since this is the lesser amount, the acid is going to react to completion, as we saw over here, because the K value is so much greater than 1. And so all of this is going to react. So we're going to end up with negative 10. We're going to subtract out 10 millimoles. We're going to use up all 10 millimoles. So it's a 1 to 1 to 1 to 1 ratio. So if we lose 10 millimoles here, we're going to lose 10 millimoles here. And we're going to gain 10 millimoles here. And we're going to gain 10 millimoles here. Now the water we don't really care about. That's superfluous. What we really care about is the millimoles of the conjugate acid and the base here. So this is going to go to 0. We don't have any acid left over. We subtract 10 from 40. We get 30 millimoles of the weak base left over. And then we end up with 10 millimoles of the conjugate acid left over. So now we have some of the conjugate acid, some of the base, so we do have a buffer at this point. So now at this point we have a few options of what to do when we to solve this problem. So stay tuned. Okay, so method number 1. What is method number 1 that you could use to solve this problem? Method number 1. Okay, so the first 3 methods are going to involve using the Henderson-Hasslebach equation. So the first one is, first, we identified this as a buffer because we have some weak base and conjugate acid in solution. And as we calculated the Ka value for the weak base or the conjugate acid, for that is we calculated, where to go? I erased it. It's right over here. So 5.55 times 10 to the negative 10. So the Ka value is very small. So therefore, the conditions for using the Henderson-Hasslebach equation are met, and so we can assume or suspect that x is going to be negligible, and we can go ahead and use the equation. Now, there's a few ways you could use the equation. The first is to convert everything back into molarities, into concentrations. So that would be the first one. So convert millimoles to concentrations. So technically, you would have to convert things to concentrations to plug it into the Henderson-Hasslebach equation, because you need concentrations, because you have the concentration of the base over the acid in the equation. So let's go ahead and do that. So we got 30 millimoles. We have the total volume is 10 milliliters plus 200. So that's going to be 210 milliliters. So you take the millimoles. So we'll do the base first. So the molarity of NH3 is going to be equal to 30 millimoles divided by 210 milliliters. The milli cancels out. We have moles over liter, and when you calculate that out, you get 0.142 molar. 0.142 molar. I know that the number sig figs is 2, but I'm keeping an extra digit to avoid rounding mistakes. And then I do the same thing with the molarity of NH4 plus. So that's going to be equal to the millimoles, 10. So 10 millimoles of NH4 plus divided again by the total volume, 210 milliliters. Milli cancels out. We got moles over liter. So the concentration for ammonium is going to be 0.0476. 0.0476 molar. Again, I'm keeping an extra digit to avoid rounding error. So now that I have the molarities, I can now plug everything into my my Henderson-Hasslebach equation. Okay, so here I go. So here I have the Henderson-Hasslebach equation. Now I go and plug everything in. So I'm going to have the pH is equal to the pKa, which again, pKa is the negative log of Ka. So negative log of the Ka value, which is right here. We calculated that before. So 5.55 times 10 to the negative 10. And then we're going to add to that the log of the concentration of base over the acid. So log over concentration of the base. So the concentration of the base is 0.142. 0.142 molar over the concentration of the acid, which is 0.0476. 0.0476 molar. And when you calculate this out, you get a pH of 9.730. 9.730. And so that would be the pH according to this method, using the calculated concentrations after we mixed everything together. Okay, now I want to point out that for the pH, we have 9.730. The pKa if I remember correctly, is going to be less than that, and the pH is going to be higher, or is going to be lower, because the concentration of the base is so much greater than the acid. Oh, sorry, I misspoke. So we would expect this to be higher because we have more base species in solution compared to the acid species. And so you would expect a pH that's going to be greater than the pKa of the acid. Okay, so that's method number one. Method number two is just use the millimoles. Why? Because if you realize that since in order to create the molarity, you have to divide both millimoles of acid and base by the same total. Well, if you put that in here, the total volume cancels out. So let's take a look at that. So let's go ahead and do the second method. So method number two is going to be just use moles or millimoles. So let me point this out more clearly. So here, if I plug everything in again, pH is equal to the pKa, which is negative log of the Ka value. Again, 5.55 times 10 to the negative 10. And then we're going to add to that the log of the acid and the base. Well, if we plug in the volumes, right, and the molarities, so we had for the base, we had 30 millimoles divided by 210 milliliters. That's how we got the molarity of the base. And then to get the molarity of the base, we took the 10 millimoles, the acid, to get the concentration of the acid, we took the 10 millimoles of the acid, divided that by, again, the total volume of the solution, and you'll notice that, look, the total volume cancels out anyway, so this cancels out with that, and you end up having 30 millimoles divided by 10 millimoles. So basically, you can get the same answer by just plugging in the millimoles of the base over the acid, and when you calculate that out, again, you get the pH is equal to 9.73? 9.730. 9.730. So you get the same answer either way. So if you want to skip the calculation part, you can skip the calculation of the molarity and just go ahead and plug in the millimoles. It might save you time on a test or quiz, so it's good to look out for that. Now, the third method, using the Henderson-Hasslebach equation, method number 3, is to note the fractional amount reacted. So when we reacted 10 millimoles of the strong acid with 40 millimoles of the weak base, we produced or reacted 1/4 of the original amount. So 1/4 of the original amount reacted to create the conjugate base, and you had 3/4 left over, so you can just use the fractional amount. So if I do that, right, so then we'd have the pH is equal to the pKa, which again is the negative log of the Ka value. So again, we'll write that. So negative log of the Ka, which is 5.55 times 10 to the negative 10, and then plus the log of the acid over the base. But if we recognize that the fractional amount that reacts, we start out with a certain amount of our base, we react a certain amount and notice, 10 millimoles is 1/4 of the original 40 millimoles. So 1/4 of it reacted, leaving 3/4 left over unreacted. So that tells us that we have 1/4 the acid, 3/4 of the base left over. So we can just use those fractions. So then we have the log of the concentration of the base, which we said was 3/4 left over. And then we created 1/4 fractional amount of the acid. So we have 1/4. And if we plug those in, right? And then notice that the 4's cancel out, but be that as it may, we plug this in and we get pH is equal to 9.730 once again. And so basically, those are the three ways in which you can use the Henderson-Hasslebach equation. One, you can just take your millimoles or your moles, use the total volume to convert that back to concentrations, plug the concentrations into your Henderson-Hasslebach equation, calculate the pH. Or you can just, instead of calculating the concentrations of your acid and base, you can just plug in the millimoles or the moles directly into the equation, since the total volume cancels out anyway, and you can get the pH that way. And then finally, if by happenstance, if you notice that there's a fractional amount, maybe it's an easy, clear fraction, a fraction of 1/2, 1/4, 1/3, you can go ahead and plug in the fractional amount and calculate the pH that way using the Henderson-Hasslebach. And then there's one last method. This doesn't involve the Henderson-Hasslebach. It is merely using your ice table. So you can also do it the other way. Go ahead and do your ice table for either the base reacting or the acid reacting with water. Set up your ice table, do the whole X is small approximation, and then you can figure out the pH that way. I'm not going to go over that one. I have plenty of videos where I go over that as well. And so that is what I wanted to cover in this video. I hope this was helpful. If it was, then please, by all means, like the video, hit that like button down there. Also, subscribe to my channel. What are you doing? Help me out. Hit that notification bell. When you do, click all so you can be notified by all the videos I put out. And finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. Thanks for joining me, and have a great day.